So now let's go ahead and look at the graphs of our logarithms. We're not going to spend a ton of time on our logarithmic graphs just because we don't see them occur or happen quite as often as our exponentials. So it's more important that we know how to graph and move around our exponential graphs. But I do want us to go ahead and kind of see what our logarithmic graphs look like. So here we have f of x equals 3 log base 10 of x plus 1. So if we go ahead and go into Desmos, we can see that our graph is almost the inverse of our exponentials. So our exponential graph would be close to our x-axis and then shoot up. Notice that this one has been reflected, so my asymptote is on my x-axis this time, and it's still increasing. It's just doing so rather slowly. So let's go ahead and look at if I just had log base 10 of x, what that would do to my function. So notice that looking at my graph, my black graph would be my parent graph, and my red graph is it with the transformations. So notice that on my black graph, I have an intercept at 1, 0. And notice that now on my red graph, we've shifted that, it's a little bit hard to tell, but to approximately 1, 1. And that's because notice this 1 on the outside has shifted everything up. And that's going to be very similar to all of our other transformations that we've seen with our other types of graphs. Now, we don't have anything on the inside, and that is really important. Anytime anything is on the inside of a logarithm, it will need to have parentheses around it. So notice that on the example they gave us, this plus 1 does not include parentheses, so we know that that's on the outside of our logarithm. And then there's a 3 to the front of our logarithm, and that's what makes this stretched or come up and away from our logarithm. So in general, if I have anything that's being added on the outside of our function, it's going to shift my function up if it's positive or down if it's negative. If we have anything on the inside, it is still going to shift it left and right, but remember, just like with our other types of transformations, because it's on the inside of the function, it's going to do the opposite of what you would think it was. So if I plug in a 3, I would have x minus 3 on the inside of my equation, which moves it to the right 3 spots. If I plug in a negative 3 there, it would become x plus 3, which moves it to the left 3 spots. And then again, my a value, or the number that's being multiplied on the outside, is going to stretch or compress it. So the bigger that it is, the farther it's going to stretch it. If it's between 0 and 1, it's going to compress it towards my x-axis. And then if it's negative, it is going to reflect it. So let's go ahead, get a copy of this graph right here. And we're going to put that in. So here's what our graph would look like. Some key things to point out. Remember that we said we've moved our graph up 1, but that means that we haven't changed where our asymptote is. Our asymptote is still going to be x equals 0. Now, if we were to move our graph left or right, that would change where our asymptote is, and it's going to change it the same number of units that we move it left or right. Okay? The other thing that's important to point out is remember that our domain this time has to be x such that x is greater than 0. Or remember that we can write that as 0 to infinity. And our range this time is going to be the all real numbers. So let's go ahead and move along. So when we're dealing with logarithms, sometimes we might need to manipulate them, either to evaluate them or sometimes to solve for a specific variable. So like on my first one, we have an x on the inside of our logarithm. It's a little bit tricky to try and figure out what that x would be by just looking at it how it is. So a lot of times it's going to be helpful for us to rewrite a logarithmic statement or equation in exponential form. So that's what we're going to do here for our first example. So remember that my base of my logarithm is still going to be our base of our exponent. So we would have a base of 36. And then remember the other key thing that I mentioned, and I will continue to mention, is that logarithms equal exponents. So this equals 3 halves. So that means that 3 halves has to be my exponent. And then whatever's on the inside of my logarithm is what goes on the right-hand side. And lucky for us, notice that just by switching it to exponential form, my x is now solved for. I don't have to do anything else. The only thing that we kind of have to do is simplify that 36 to the 3 halves. But we've dealt with things like this before. Remember that anytime that I have a power, we could break this apart. Notice that I have a 1/2 and a 3. And the reason that I do that is because remember, if I raise a power to another power, I multiply. Which also means that if I wanted to go ahead and break it apart using multiplication, I could. And again, the reason that I did that is because remember that raising something to the 1/2 power is the same thing as taking the square root. And we know what the square root of 36 is. I might not necessarily know what 36 to the 3 halves is, but I know that the square root of 36 is 6. And then we could raise that to the 3rd power. And 6 to the 3rd is going to be 216. And that would be our answer for that first question. Now our second example is a little bit different because notice we don't have a variable. And so we're not solving for a variable. However, what we want to do instead is say, okay, we're trying to evaluate this. Well, I don't know what that is, and we haven't dealt a ton with logarithms, so it's kind of tricky to just say what that is. So what we're going to do instead is we're going to say, okay, I'm going to set this equal to some variable. And in this case, I'm going to use an x. Well, now we do have an x to solve for. And again, we're going to use that same technique of, okay, I'm going to switch my logarithmic form to an exponential form and see if I can solve it from there. Again, remember, my base of my logarithm becomes my base of my exponent. Then logarithms equal exponents. So that means that x is going to be our exponent. And that's going to equal 4. Well, x is in our exponent. That's a little tricky. However, we just got done going over our exponential equations. And remember that the key for our exponential equations is if I can get my bases to equal the same thing, we can just rewrite and put our exponents equal to each other. So in this case, I have a 4 and I have a 16. And hopefully we can kind of see that 16 is going to be 4 squared. When we raise a power to another power, we multiply. So we end up with 4 to the 2x equals just 4. Well, and it might be a little bit hard to see because now I have my bases the same. And we know we have a 2x. But what are we supposed to set that equal to? And we have to recall back that anytime I don't have an exponent, it's an understood 1. So we would solve for x and get 1/2. So now we know that we could state that log base 16 of 4 equals 1/2 by plugging that 1/2 back in. And then lastly, the last place that we could see an x or need to solve for something would be as if it's in our base. And so again, we're going to start by rewriting this in exponential form. So remember that the base of our logarithm is the same as the base of our exponents. Logarithms equal exponents, so my exponent is going to be 5/3, and then that's going to equal whatever's on the inside, which is 32. And from here, it's just going to be any of our other types that we have. Whenever we raise something to a power, we need to undo that power. So we have kind of two things going on here. So again, I'm going to kind of break this apart into 5 times 1/3. That way then we only have to deal with one of those exponents at a time. So remember that the 1/3 is the same thing as taking the third root of something. So in order to undo taking the third root, we would raise both sides to the third power. And 32 to the third power is going to be 32,768. And I would just use a calculator for that. Okay, and then now we have x to the 5th. Well, we've dealt with equations like this before. If I have a 5th power, the way that we undo this is by taking the 5th root of both sides. Again, plugging this then into my calculator. We get that x equals 8. You also could have done this the opposite way and taken the 5th root first, and you would have gotten 2, and then raised to the third power and gotten 8, because 2 to the third is 8. So now we've kind of looked at how to solve for a missing piece, no matter where our variable might be. Okay, the last thing that would happen is, say we have logarithms on both sides of our equations. That's going to be a little bit different because we can't convert that to exponential form. But lucky for us, there's a similar property to what we had with our exponentials, and that is our property of equality for logarithms. And basically what it says is, long as my bases are the same for my logs, the inside of my logs have to be the same as well. So in the example that they give, we have log base 5 of x equals log base 5 of 8. Since both of my logarithms have a base of 5, we can just set our insides equal to each other, and we get 8. However, it is going to be very, very, very important, again, that we check our solutions. And the reason for that is because, remember, if I have log base anything of x, that x has to be greater than 0. So basically we need to check and make sure whatever we're plugging in and we get inside of our logarithm, it has to be positive because of that domain restriction. So let's look at an example. We have log base 2 of x squared minus 4 equals log base 2 of 3x. So notice that we have a log base 2 on both sides, which is handy because our bases are the same. Which, remember, as long as our bases are the same, just like with our exponentials, that means that we can just look at the inside of our logarithms being equal to each other. And from there, hopefully we notice that I have an x squared, which means that this is going to be a quadratic. So I'm going to move everything over to the left-hand side so that I can get it set equal to 0. Because then remember, from there, if I get it set equal to 0, we can either factor it if it's factorable, or use our quadratic equation if it's not factorable. So in order to factor it, I'm going to use our AC method, but you could use whatever method you feel most comfortable with. But for me, I'm looking to see what multiplies together to give me a -4, that adds together to give me a -3. Well, that's going to be a -4 and a +1. And then we're going to set each of our answers equal to 0. Well, notice that we get 2 answers, but this is a multiple choice question. And notice that -1 and 4 are both options, but neither one of them is an option to have both of them at the same time. And this is where I said it's going to be really important that we go back in and we check ourselves. So I'm going to start with our original equation, and that's going to be really important. So we still have log base 2. I'm going to go ahead and plug 4 in. So we would have 4 squared minus 4 equals log base 2 of 3 times 4. Well, 4 squared is 16. 16 minus 4 is going to be 12. And 3 times 4 is also 12. So notice that that one checks out. Well, we're going to go ahead and check our other one because, hey, maybe there's a mistake in the question. Maybe both of them should work. So again, I'm going to go in and say, okay, -1 squared minus 4 equals log base 2 of 3 times -1. So -1 squared is going to give me 1. 1 minus 4 is -3. And then -1 times 3 also gives me a -3. So technically, we get a true statement because they equal the same thing. However, because we have a negative on the inside of our logarithm, we would get a domain error. So that means that -1 cannot be one of our solutions. So that means that only 4 is going to be able to work. So that's going to be my solution. Now let's say if we had a problem where like -1 was our only solution and it didn't end up working, then you would just say that there is no solution. Otherwise, you would just use the other solution like we did here. So make sure that you look over these notes and let me know if you have any questions or kind of need any clarifications on any parts. Also, it's going to be really important that you do those practice problems and your homework problems because it's going to take a little bit of time to get used to this new idea of logarithms.